The ability to construct our own composite data types lets us cleanly represent sophisticated data structures in our code. But there are some challenges that come with that ability. Let's take a look at the example of the queue data structure. Abstractly, a queue stores a collection of elements and supports two operations, enqueuing and dequeuing. The enqueue operation adds a new element to the queue, and the dequeue operation removes an element from the queue, following the invariant that elements are dequeued in the same order that they were enqueued. Given that definition, how would we write code to represent a queue? A natural choice would be a list, which is a data type that can store a collection of elements. We could define an empty queue to be an empty list. Then we could define a function that performs the enqueue operation, enqueuing an element onto a queue, returning an updated queue. We'll achieve that behavior by using the append operator to add the element to the end of the list. Likewise, we could also define a function to perform the dequeue operation. It accepts a queue as its argument and returns a pair of the dequeued element and the updated queue. If the queue is empty, then there's no element to dequeue. We can raise an exception here. Otherwise, we'll return the head of the list, which we know must have been enqueued before any of the other elements in the list, and we'll return the tail of the list as the remaining queue. Using these values, empty queue, enqueue, and dequeue, we can write code to work with a queue data structure. For example, we might start with an empty queue, enqueue the number 2, then the number 4, and then the number 6. Now, if we were to call the dequeue function on our queue, we'd see that the first dequeued element is 2, and leaves us with a remaining queue. If we dequeue from the remaining queue again, we see that the next dequeued element is 4. The queue operations work as expected. Elements enqueued earlier are also dequeued earlier. That said, since we're using a list here to represent our queue, it's possible that we could write code that causes the queue to behave in unexpected ways. For example, what if we had the empty queue, enqueued the number 2, 4, and 6, and then tried to reverse the list? Since our queue is just represented as a list, this code works, but it's broken the invariant that elements enqueued earlier are dequeued earlier. When we dequeue from this queue, we see that we no longer get 2. The problem here is that queues should really only support two operations, enqueuing and dequeuing, but lists support many operations, many of which are inappropriate for queues. Operations like reversing a list, mapping over lists, taking the nth element of lists. We could document the fact that we should only use the enqueue and dequeue operations, but it would be much better if we could enforce what operations can be applied to the data and prevent any inappropriate operation from being used at all. The solution will be to use an abstract data type, where we define a type that provides both a concrete implementation of the data type and its corresponding operations, but also provides an interface to the data type that enforces that only certain operations can be used on this data type. If we were to build a queue as an abstract data type, users of our queue data type would have access to the interface and would know that they can create empty queues, enqueue, and dequeue, but the underlying implementation details, namely the fact that the queue is implemented as a list in this case, is not exposed in the interface. It's hidden behind an abstraction barrier. This satisfies the edict of compartmentalization. Limit information to those with a need to know. Users of our queue don't need to know that it's implemented as a list. All they need to know is what operations are allowed for queues specifically. So let's try to build an abstract data type in OCaml by providing both an implementation and an interface. We'll start with the implementation. We implement abstract data types in OCaml via modules. Modules are a way of packaging together types and values. To define a module, we start with the keyword struct and end with the keyword end. In between go all of the definitions of the types and values that make up the module. We can even give the module a name with the module keyword followed by a name for the module we're defining. So with this knowledge, let's build a module for representing a type for queues of integers. We'll define a new module called int queue. The module definition always starts with the keyword struct, And inside the module, we define types and values. For example, we could first define a type int q, which will be implemented in this case as an int list. We'll define a value empty q, whose type is int q, and it will be equal to the empty list. And we'll also define our functions nq and dq, which are the same as the functions we've written before, but now they're using our int q type that we've defined in this module. And finally, we'll end our module with the end keyword. This module packages together values and types. It contains a type int q, a value for the empty q, and function values for enqueuing and dequeuing. Once we've defined a module, we can use it. To use a module, we can use dot notation. We use the module name, followed by a dot, followed by the name of the component of the module we're trying to access. So we could define a queue to be the result of taking an empty integer q, enqueuing 2, enqueuing 4, and enqueuing 6. One thing you might notice here is that we're repeating ourselves quite a lot. If we're using the same module many times, we'll end up repeating the module name in our code frequently. Instead, we can open the module, which lets us gain access to all the components of the module without needing to name the module every time. If you experiment with writing a module like this yourself, you might also notice that we haven't actually solved our problem. Our whole goal with modules was to limit the operations that could be performed on queues to only the appropriate ones. But nothing stops us from taking our int q type and performing some inappropriate operation, like reversing the list, which would result in us dequeuing the wrong element. What's going on here? Recall that an abstract data type involves both the implementation, the actual types and values we're using that are defined in the module, as well as the interface, a specification of what users of our module are allowed to access. Defining a module provides us with the implementation, but we haven't yet provided an interface that limits what users of our module can access. In OCaml, we specify that interface via a signature. A signature determines what components of the module are allowed to be accessed by users of the module. The notation for signatures looks similar to the notation for modules. A signature begins with module type, followed by the signature name. Then we start the definition of the signature with the keyword sig, followed by the definitions of the values and types in the signature, and then the keyword end. So here's what a module signature for integer q's might look like. We define the signature int q, using all capital letters by convention for signatures. Following the sig keyword, we'll specify that the signature for this module includes a type int q, a value empty q whose type is int q, and functions enqueue and dequeue. For any module that's constrained by the signature, users of the module will only have access to what's provided by the signature. They'll have access to a type int q, but notice that the concrete implementation of int q isn't in the signature. Nowhere in the signature does it say that int q is implemented as an int list. So users of the module won't be able to treat int q like a list. They'll only be able to use the operations that are provided by the signature itself. The only remaining step then is to connect the int q module we wrote originally to the signature we've just written to constrain it. The syntax for that looks a lot like the syntax for notating the type of a value. We'll use a colon after the name of the module, followed by the module signature name. Here we're defining a module int q that is constrained by the signature int q in all caps. So even though the module has implementation details, like the use of int list to represent our queue, that won't be available to users of the module because it's not exposed by the signature. And if there were functions or other values defined in the module that weren't included in the signature, those values wouldn't be available to users of the module either. Let's see what actually happens when we try to use the module. We can create an empty queue and enqueue some values, same as before. But if we were to try to treat the queue as a list and call list.rev or some other list function, we'll get an error. The function is expecting a list, but we've provided an int q. This error is actually good. The fact that int q is implemented as a list shouldn't matter to the user. The user of the module shouldn't have access to that implementation detail. It's behind the abstraction barrier. And because of that, we've made it impossible to use any kind of inappropriate operation on our queues, all just by creating an abstract data type with an implementation provided by a module and an interface provided by a signature. We've defined this module to work with integer lists, but we could have made it polymorphic as well. Instead of defining a signature that specified a type int q, we could have instead specified a polymorphic type alpha q. And then in our module definition, we would implement our alpha q type as an alpha list. Let's take another example. One abstract data type that might be useful to us is the set. Speaking abstractly, sets store a collection of unique values. So we can add elements to sets and check whether an element is a member of a set, but there's no notion of order. There's no first or second element, for example. Here's what a module signature might look like for an abstract data type for representing sets of strings. We define a type set and a value for an empty set. We also have a function that takes a string and adds it to a set, a function member that takes a string and checks whether or not it's in the set, and a function union that takes two sets and combines their elements together to create a new set with all of the elements. You could imagine that we might also have other functions to define operations for sets, functions to check if a set is empty, to take the intersection of two sets, to remove elements from a set, and so on. But for simplicity, we'll just use these three functions for now. In order to actually use this string set data type, we need to define its implementation via a module. So here's a module for string sets that satisfies the string set module signature. We need to define what type we're going to use for representing a string set, so let's use a string list for simplicity. We'll need to maintain the invariant that the list doesn't have any duplicate values in it, but we don't need to worry about the order values appear in the list. The empty set we can define as the empty list. Now we'll define a function for checking if an element is a member of a set. For this, we can just use the list.mem function. It's a function that checks if an element is a member of a list, and since our sets are implemented as lists, we can use list.mem from inside the module definition. In order to add an element to a set, we can first check to see if the element is already in the set by using the list.mem function again. If the element's already in the set, then we can leave the set unchanged. Otherwise, we'll add the element to the set. Since the order doesn't matter, we can add it to the beginning. And to take the union of two sets, we can just fold our add function over the set. Taking the union of two sets is essentially the same thing as adding each of the elements of one set to the other set. And since the add function already handles making sure that there are no duplicates, we now don't have to worry about duplicates in the union function either. With this module signature and module definition, we've defined our abstract data type for string sets. We could use the module to take an empty set and then add some strings to it. We could then check to see if a particular value is a member of a set. This implementation works, but there are a few areas for improvement we might notice. The first area for improvement comes from the efficiency of our set operations. We represent sets as lists, but those lists aren't necessarily in any particular order. As a result, when we add elements to a set, we need to check over every element in the list to make sure there aren't duplicates before adding an element. That becomes especially inefficient when we take the union of two sets. We end up going through each element of one set repeatedly for each element of the other set. As we start dealing with larger sets, we may want to make our implementation more efficient by implementing sets as sorted lists instead of unsorted lists. With a sorted list, we won't need to look through every element in the list in order to add a new element. We can stop once we get to where the element would belong in sorted order. So let's give that a try by rewriting our module definition. Note that nothing in our module signature is changing. The same operations are still used for sets, we're just changing how those operations are implemented in the module. To check if an element is a member of the set, we'll match the set. It's implemented as a list, so if it's an empty list, the element isn't a member and will return false. If there's a head and a tail, we'll check to see if the head matches the element. If so, we found the element in the set and we return true. Otherwise, if the element we're looking for belongs before the head in sorted order, then we can conclude the element isn't in the list at all. We'll return false. And otherwise, we'll check to see if the element is a member of the tail. The story for adding an element is similar. We can't just add the element to the beginning of the list, so we'll instead traverse the list until we find the correct position for the element, such that the list remains in sorted order, and we'll insert the element there. Our implementation of sets is now more efficient, achieved by changing the underlying implementation of the set. And the added beauty of what we've just done is that nobody who uses our set module needs to know that this change has happened. None of the code that uses the set module needs to change at all because the interface hasn't changed. All the same operations are possible, and the underlying implementation details are behind an abstraction barrier. Another area for improvement you might notice is that this module and its corresponding module signature only work for string sets. What if we wanted a module signature for a different type of set, say integer sets? We could write a module signature for integer sets, but this of course violates the edict of irredundancy. We've essentially written the same module signature twice. The only difference is what type we're using for the element. Instead, let's define a generic signature for set modules that we could use no matter what the element type is. In this generic set signature, we'll define a type for a set, but also define a type for an element. Functions like add, instead of taking a type like string or int as its argument, will instead take our element type as its argument. This generic signature is designed so that it can be used no matter what the type of the element of the set is. So what would happen if we tried to define our string set module again, but this time constraining it to the generic set module signature instead of the more specific string set module signature? We run into a problem right away. Watch what happens if we try to add a string to an empty string set. We get an error. The expected argument type is element, but we've provided a string. What's going on here? Remember that when we use a module, the only thing the user of a module has access to is what's provided by its signature. Here's that set signature again. Notice that as users of a module constrained by this signature, we know that there is a type called element, but we don't have access to the detail that element is really a string. That's behind the abstraction barrier. Compare that to the string set signature we were using before, where the string type was used in the specification of these values. We knew that we could pass these functions arguments of type string. So we have a problem. We want to use the more generic set signature so that it works with multiple types, but the abstraction barrier is too strict. The signature is hiding too much. It's not sharing what the type of element is, and we need to know what the type of element is in order to provide values of type element as arguments to functions like member and add. So what do we do? The solution is what's known as a sharing constraint. When a module signature is too abstract, when it hides some information we need to know, we can add a sharing constraint to specify how an abstract type is implemented. In this case, the set signature doesn't share the necessary information that the type element should be a string. So we'll define a signature string set to be equal to set with the sharing constraint that type element equals string. We're augmenting the set signature with some additional piece of information, that elements are strings. We haven't eliminated the abstraction barrier completely. The user still doesn't have access to other implementation details, like how the set itself is implemented, but they do get the necessary information that for sets of strings, the element type should be string. Using sharing constraints, we can use our generic set signature to define signatures for specific set types. We could define a signature for string sets a signature for integer sets, a signature for sets of pairs of integers and Boolean values, and so forth. But just defining the module signature isn't enough to actually give us abstract data types for all of these different kinds of sets. Recall that we need both the interface provided by the signature and the implementation provided by the module. We already have an implementation for string sets, but if we wanted to create an abstract data type for integer sets, we'd need an implementation for integer sets too. What would that look like? Well, it would look very similar. Here's an implementation for integer sets. And one thing you should notice immediately is that it looks very similar to the implementation for string sets. And that'll be true for other types of sets we define too. Every time we write the same implementation, we're violating the edict of irredundancy. So what should we do? The first thing we can do is look for where set implementations will differ. One obvious place they will differ is in the type of the element. For integer sets, the element type is int, but for other types of sets, the element type will be different. Another less obvious place where the implementations might differ is when we compare elements to figure out where they belong in sorted order. For integers and strings, we can just use the built-in less than operator, but that won't necessarily be appropriate for all types. For different types, we might want some different function used to perform the comparison. So what are we looking for here? In order to avoid redundancy, ideally we'd like a single mechanism that takes a type like int and a comparison function like the built-in OCaml compare function, and then generates an integer set module. And if we provided the mechanism with a type like string and a comparison function, it would generate a string set module, and so on for other types too. First, how would we even represent the idea of packaging together values and types like this? Well, that's what modules are, combinations of values and types. So you could imagine defining a module that defined a type and a comparison function. Now, what we really want is something kind of like a function that accepts a module as input and uses that to generate the module we want. OCaml has a way to do this, and it's called a functor, which essentially acts like a function that accepts a module as input and generates a module as output. Let's try to write a functor then for generating set modules of any type we want. First, what will be the input to the functor? It's going to be a module that combines a type with a function for comparing that type. So let's define a signature for this argument module. We'll call it ordered type, and it will contain a type t and a function compare that takes two values of the type and produces an integer, -1, 0, or 1, depending on whether the first element is less than, equal to, or greater than the second element. Now let's define our functor makeOrderedSet. MakeOrderedSet is going to be a functor that takes a module as input. We'll call that module elements, and it's going to be a module satisfying the ordered type signature. This argument will contain information about what type to use for the set, as well as how to compare elements of that type. The output of the functor will be a new module satisfying the set signature. This is the module we actually want. And since we know we also need to add a sharing constraint so that users of our set module know what the element type is, let's do that now. We'll share what the type of the element is, but what is that type? Well, it's whatever type is defined as type t in this argument module elements. So we'll use elements.t as the type. Now we can define the module itself. It's pretty similar to what we've written before. This time, though, the type for each element will be elements.t, using the type provided by the input module elements. And in our member and add functions, we'll use the elements.compare function to perform the comparisons between elements, and we'll use the results of that comparison function to decide what to do next. There's a lot going on here, so let's briefly review all the parts. MakeOrderedSet is a functor. It's going to take a module as input and produce a module as output. The input is a module that we're calling elements, and it satisfies the ordered type signature. which tells us that the input module is specifying a type t and a comparison function called compare we can use to compare elements of that type. And the output of the functor is going to be a new module that satisfies the set signature. The set signature alone doesn't share what the type of elements in the set are, which means users wouldn't ordinarily be able to add elements to the set or check membership in the set without having access to that type. So we add a sharing constraint so that the user does have access to the element type, defined as whatever the element type is in the elements module. There's a lot going on here, but the end result is we have a way of generating modules based on other modules. We can generate a string set module by applying our makeOrderedSet functor to a module that defines the type to be string and uses a comparison function. And we could do the same for integer sets or any other type of set that we'd like. These abstract data types can solve a lot of problems for us. They allow us to separate the implementation of a data type from the interface to the data type. As a result, we can ensure that only the operations we want are permitted for the data. And we can ensure that if the implementation of the data type ever changes, users of the code are unaffected. The implementation details are behind an abstraction barrier, so as long as the interface stays the same, all of the code that uses our abstract data type will still work perfectly.